So, like here's a salt crystal, sodium chloride. We know you drop salt into a glass of water, it spontaneously dissolves. The chloride ions get surrounded with water molecules. And notice how it's the positive hydrogen inside of the water molecules that are attached to the negatively charged surface. If you go over and look at the sodium ions, it's the other way around. It's still hydrated, but it's the negative oxygen end of the water molecules that's interacting with the positively charged sodium. These are charged, in other words, they're charged dipole interactions. Not charged-charged, but charged dipoles. What about non-ionic things like a glucose molecule? Well, look at this. Glucose is just a series of these hydroxyl groups. And OH, you've got a hydrogen attached to an electronegative oxygen. That can form a hydrogen bond, right? So it can interact with water even though it's not charged. It can form hydrogen bonds, and it does. So anything that's polar, this is a polar atom because it's got heteroatoms like oxygen and nitrogen and sulfur. Polar groups like that dissolve readily in water. So anything ionic dissolves well, anything polar can form hydrogen bonds, dissolves well. And what's your retention of information? What do we call that? Interaction of sodium by water. What kind of?
Oh, that charge.
Charge, not hydrogen, because this, no.
And what was the chloride again?
Chloride, and here's the big one's chloride. It's negatively charged. Which face of the water molecule it likes to interact with the positive hydrogen, the blue hydrogen?
Yes. So that would be called.
That's a charged dipole interaction. The water molecule is a dipole. It's just a question, is it pointing this way or that way? In this orientation, the positive face is interacting with the negative charge, and that's stable. If you go over to the cation, the sodium ion, it also does a dipole interaction, but it wants the negative side of the water molecule.
And then that would be a negative charge?
Yeah, they're both called charged dipole.
Oh, okay. Okay.
And the interaction, what interaction is involved when you dissolve glucose in water? Hydrogen bonds. Okay, so that takes care of a whole lot of the metabolites and macromolecules in our cells, between the polar guys and the ionic molecules. But what about lipid-like molecules, the fat-like molecules? That's the one area where water isn't very good. Water is often called the universal solvent, but it falls down when it comes to non-polar hydrocarbon-like molecules, like cholesterol, like fats, and so on. So they only have limited solubility of water. They form these cage-like structures and hide in them unless they are mixed in character. And this is an important subcategory of lipid molecules. This is a so-called fatty acid. It's a component of the membrane fats and storage fats. It's got this pure hydrocarbon tail, as it's called, plus a polar head group that's a carboxylic acid. Notice its charge. This is where it would sit in a membrane-water interface. If this is water up here, that carboxylic acid loves to be interacting with the water through charged dipole interaction. The fatty acid tail would hide away from the water as best as it could. Something with mixed character that's both polar on one side, non-polar on the other is called amphipathic. That was the question you were asking about before. So these kinds of molecules form monolayers.